Welcome to Unit 7, Cartesian Vectors, Lesson 4, Vectors in 3 space. So far we've only looked at vectors in 2 space, geometric vectors, and up to Lesson 3. But now we're going to explore vectors in 3 space. So 2 space is abbreviation for two-dimensional space. You're familiar with illustrating points in 2 space. We've done that since grade 9. On our Cartesian plane. The two dimensions are defined by the x and y axis, making an xy plane. So here I have, of course, the x-axis here, and I've got the y-axis here. A two-dimensional graph has 4 quadrants. Both the x and y coordinates are positive to the top right, so here's the first quadrant, and this is called, of course, the first quadrant. Whoops. And the other continuing in a counterclockwise direction. So the first quadrant, second quadrant, third quadrant, and fourth quadrant. To place a point at -2, 4, like we've done in grade 9, I go 2 to the left, and then 4 up, and so this point here is what I call my point A. If I want to place a point at 0, -2, so there's no horizontal movement, but there is vertical movement. I'm moving down 2, and so this would be my point B. Now, here we go, 3 space. 3 space is an abbreviation for three-dimensional space. You're probably not familiar with illustrating points in 3 space. The 3 dimensions are defined by x, y, and the new axis, which is z. So here x is coming towards you, y is that kind of that horizontal, and then z is going up. The negative part of each axis is shown with a dotted line. So here this is positive x, over here this is negative x. Positive y, positive z, and negative z. The right hand system helps you orientate the axis correctly. If you curl your fingers, so your right hand from the positive x-axis, which is your index finger, your middle finger is the y, and of course the z is then, your thumb is then pointing up in the z-axis. A 3D graph has 8, not quadrants anymore because quad is 4, but octants, that's 8. The first octant has points with all 3 positive coordinates. X, y, and z are all positive. There's no agreement on the other 7, but we know where the first one is. So for instance, if I wanted to graph the point 1, 2, 3 and label it A. So just like before, I'll do my A first with my x first. So I've got x, so it's at 1. Then my y is 3, so y again will be going this way, but I'm going to put it over here. So that's my y going in the positive direction horizontally. And then finally 3 is z, so I'm going to go up 3, and so this coordinate right here is my point A. Notice how it's very hard to draw. I'm trying to draw a 3-dimensional point in 2-dimensional space. This is as good as we can get it. We can't do much better than that. Place a point at 2, -3, 0 and label it B. So again, I'm going to go out 2, or the positive on my x-axis, there's 2. And since y is negative, I'm going to go to the left instead of the right, so I'm going to go over to the right 3. And then my point B is right here. There is no z, so I'm not going up and down, so this is my point B. I'll leave you to try these 3 if you want to see solutions. There are solutions on the class website, but A, B, and C, so plotting those points. I'm not really big into plotting them because, again, we're trying to plot a 3-dimensional point in 2-dimensional space, so it never works out very well. All right, 3-dimensional Cartesian vectors. A position vector in 3 space has its tail at the origin and its tip at the point B, so P. So here's the first one. So here is, again, you can see here that the tail is at the origin, the tip is here. So this point right here would be called point x, y, z, and so that I would call this my vector either OP, or we'll call that my vector V. The magnitude of vector V is just the coordinate squared, so x squared plus y squared plus z squared, the sum of them, and then square root them. There are 3 unit vectors here on this, just like before with 2, but we've got 3 now because we have 3 axes. The first one, that guy here, is my vector I. Then I've got the one on the y-axis, so here, so that is my vector j, unit vector j. And then I've got the one on the z-axis, so here we call that the vector, not z, whoops. We call that vector, sorry, k. All right. Putting it together, so here I've got vector u, so it goes to the point a, b, c, so right here. We can write it in terms of its components, so now we've got three components because we've got 3 dimensions, so a, 0, 0, 0, b, 0, and then 0, 0, c, or in terms of the unit vectors I, j, and k, ai plus bj plus ck. Key concepts in 3-space. If I give you points P1 and P2, I know vector P1, P2, I just simply, just like we did before, x2 minus x1, y2 minus y1, and now we've got this new z2 minus z1. Magnitude of vector P1, P2, so we just, again, just like before, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, so that is the new part right here of the magnitude of the vector. If I give you two vectors, two unit vectors u and v, and a scalar k, u plus v is just the first coordinates added up, comma the second coordinates added up, comma the third coordinates added up. Ku is really equal to ku1, ku2, and ku3, where ku is a collinear, which also means, of course, a scalar, which we can see here, or parallel with vector u. The dot product, u dot v, so again, multiply the first coordinates together, the second coordinates together, add them, third coordinates together, add them, just like before, except we've got this u3, v3. To find the angle is the same thing. If theta is 0, so u dot v is equal to magnitude of u, magnitude of v cos theta. So again, we can change this to cos theta is equal to u dot v over magnitude of u, magnitude of v. And if u and v are perpendicular, we're going to have a new word for it. We call them orthogonal. That means that u dot v is equal to 0. And again, same thing as before. So again, we use this new word orthogonal, so that's our new perpendicular word for 3-space. We also know that if, if u dot v is greater than 0, that means the angle between is between 0 and 90. And if u dot v is less than 0, angle between is between 90 and 180. So here we'll do example 4 and 5, and then 6 and 7. Now where's 1, 2, 3, Mr. Wills? Well, I just went right into example 4 for no particular reason. We'll do 4 and 5 on this video, and the next video we'll then do 6 and 7. So here, find A such that 1, 2, 3 is collinear with 2A6. So if they're collinear, that means the ratios of each coordinate is the same. So here I'm going to write them as the first coordinates together, so 1 over 2. So I took this one, and I took this one, wrote them as a ratio. Then I'm going to do the next one, 2 over A, and do the next one, so this is going to be 3 over 6. I want to solve, of course, for this one here, and I can use either the first or the last ratio because I know the numerator and denominator to solve. So I'm going to use the first one because it's nice and easy. 1 over 2 is equal to 2 over A. So I cross multiply, so A is equal to 4. So when A is 4, the two vectors are collinear. If A is not 4, then they're not collinear. We'll continue with the next one. So here's the next one. Find A such that, no, it shouldn't say A, it should say B and C. So find B and C such that this vector is collinear with this one. So again, we're going to write the ratio, so negative 2 over C is equal to B over 6 is equal to 7 over 21. So the vector I do know here is this guy here. I know the numerator and denominator, so I'm going to choose one of these, write it as a ratio and solve. So I'm going to I'll do the first one. So negative 2 over c is equal to 7 over 21. Cross multiply it, so this guy goes up here, this guy goes up here. So I'm going to have here negative 42 is equal to 7c. So c is equal to negative 6. There's the first one. We'll do the other one. So I'm now going to set it equal to the middle one. So I'm going to have b over 6 equals, again, still using that 7 over 21, cross multiply. So I'm going to have here 21b that's a 6, by the way, whoops. 21b is equal to 42, divide both sides by 21, I get b is equal to 2. So when b is equal to 2 and c is equal to negative 6, the two vectors are collinear. Example 5. Given the points A and B, express AB as an ordered pair. So again, we're going really back to two space here. So AB, the vector AB, I just do x2 minus x1. So here negative 1 minus 3, comma, 0 minus 6, y2 minus y1, and then z2 minus z1. So this is really going to give me vector AB is equal to negative 4, negative 6, and 6. So there is my vector AB as an ordered triple. It's now a position vector where its tail is at the origin. Express AB in terms of I, J, and K. So here, vector AB is equal to, take the first coordinate, so negative 4, and it is the scalar of I. Take the next coordinate, so negative 6, it is the scalar of j. Take the next coordinate, so positive 6, and it is the scalar of k. And there we go, I've expressed it in terms of I, j, and k, unit vectors I, j, and k. In terms of the magnitude of AB, so to do the magnitude of AB, I square and sum, so negative 4 squared plus negative 6 squared plus 6 squared. So here, if I do that, 16 plus 36 plus 36, this is going to give me the square root of 88. If I wanted to simplify that radical, it really would be 2 root 22. The last part of the examples is to determine the unit vector in the direction of AB. Since it's in the direction of AB, so direction, that means I'm going to do the positive unit vector. If it was in the opposite direction of AB, then I'd use the negative direction vector, or unit vector, sorry. So here we go. And by the way, the formula for this, I already wrote this out in a previous lesson, I believe, but the formula for a unit vector is 1 over magnitude of u times vector u. So this is a scalar times the vector, so we just multiply it in. So in this case, we're going to use this formula here. So we need to find the magnitude of AB. I've already got the magnitude of AB, though, from the previous question. So the magnitude of AB is really equal to 2 root 22. So unit vector in the direction of, so here's my unit vector. It will be 1 over 2 root 22, and then I'm going to write it as negative 4, negative 6, and 6. So multiply it in. So here I'm going to have negative 4 divided by 2, so that's going to be negative 2 over root 22. And it's going to be negative 3 over root 22. And then it's going to be 3 over root 22. Again, if I wanted the opposite direction, so this is in the direction, but if I wanted the opposite direction, I would just put a negative here, and so all these signs would just change. But if we found the magnitude of this, we would see that the magnitude of that is 1. We'll continue with examples 6 and 7 on the next video.